Right now, more than 30 meters under the bed of the Yangtze River, a machine longer than a football field and a half is chewing through mud, sand, and clay at a speed of about half a meter an hour. It hasn't stopped in months, and when it finally breaks through on the other side, China will have finished something no country on Earth has ever built before. A road tunnel stretching 39 kilometers. More than 11 of those kilometers running directly underneath one of the widest, most powerful rivers on the planet. No bridge, no ferry, no surface crossing of any kind for over 11 straight kilometers. Just a tube, buried in river mud, carrying 6 lanes of traffic in total darkness, beneath hundreds of ships a day passing overhead, completely unaware of what's moving underneath them. This is the Haitai Yangtze River Tunnel. And the strange part of this story isn't the size of it, it's why anyone would choose to build something this difficult, this expensive, and this dangerous to construct, when a bridge, sitting right there on the surface, would almost certainly have been simpler. This video is going to break down exactly what this tunnel is, how you dig something this size under a moving river without the whole thing collapsing, why bridges eventually stopped being good enough for this stretch of China's coastline, what's actually happening underground right now as you're watching this, and what could still go wrong before a single car ever drives through it. By the end, you'll understand why one of the most boring-sounding categories of infrastructure in the world, a highway tunnel, might actually be one of the most technically extreme things being built anywhere on the planet right now. Let's start with the river, because you can't understand this tunnel without understanding what it's fighting against. The Yangtze is the third longest river in the world. It cuts across China for more than 6,000 kilometers from glaciers on the Tibetan Plateau all the way to the East China Sea. But the part that matters here isn't the length, it's the mouth. Near its final stretch, where the river widens out before spilling into the sea, the Yangtze isn't really a river anymore in the way you'd picture one. It's closer to a moving inland sea, multiple kilometers wide in places, powerful currents, and constant ship traffic. One of the busiest shipping corridors on Earth, feeding cargo in and out of Shanghai, one of the largest ports on the planet. Think about what that actually means for anyone trying to build across it. You're not just crossing water, you're crossing one of the world's most heavily used maritime highways, while the water beneath your structure never stops moving, and the riverbed itself is made of soft, shifting sediment instead of solid rock. For centuries, the answer to crossing a river like this was simple. You take a boat. As China industrialized, boats weren't fast enough, so engineers turned to bridges, and China has built more river-spanning bridges over the Yangtze in the last 3 decades than most countries have built in their entire history. Suspension towers taller than skyscrapers, cable-stayed spans stretching over a kilometer between supports. It became almost a national specialty. So here's the obvious question. If China is already the best in the world at building river bridges, why did they choose, for this exact crossing, to go underneath the river instead of over it? That question is where the story actually begins. The tunnel connects Haimen District in Nantong City to Taikang City in Suzhou, 2 cities sitting on opposite banks of the Yangtze near its estuary, right at the doorstep of Shanghai in the Yangtze River Delta. This isn't rural farmland. It's one of the most economically dense, most heavily populated, most industrially active stretches of coastline in the entire country. Millions of people, massive shipping traffic, an enormous concentration of factories, ports, and logistics networks that all depend on moving people and goods across that river efficiently. Here's the first problem with a bridge, in this exact spot. The estuary is wide, really wide. A bridge spanning it would need towers rising far above the water, cables stretched across enormous distances, and critically, a minimum clearance high enough for massive cargo ships to pass underneath, safely, 24 hours a day, without exception. That clearance requirement matters more than people realize. The taller and longer a bridge needs to be to clear shipping traffic, the more exposed it becomes to something else entirely, weather. Typhoons move through this stretch of coast regularly. A structure that tall, sitting out over open water, needs enormous engineering margins just to stay operational. And even then, extreme weather can force closures, disrupting the exact traffic flow the crossing was supposed to guarantee in the first place. A tunnel doesn't have that problem. Weather at the surface doesn't touch something buried 30-plus meters below a riverbed. A typhoon can be tearing through the region, and traffic underground just keeps moving. There's a second, quieter reason too. Shipping lanes near a major port like Shanghai are precious real estate. Every bridge pier placed near a shipping channel becomes a permanent obstacle ships have to navigate around for the rest of that bridge's operational life. In one of the busiest port approaches on the planet, planners increasingly want to avoid putting anything into the water at all. A tunnel puts nothing in the water. The river surface stays completely untouched. Ships passing overhead never even know it's there. So the logic starts to come together. A wide estuary, severe weather exposure, and an extremely sensitive shipping channel. Put those three pressures together and the case for tunneling instead of bridging gets a lot stronger. But knowing you want a tunnel and actually being able to build one are two very different problems, because tunneling under a riverbed at this scale had never really been attempted anywhere at this length, this diameter, and this depth. To understand why this project is so extreme, it helps to understand how tunnels have traditionally been built. For a long time, tunneling meant one of two things. You dug from the surface downward and covered it back up, which only works in shallow, accessible ground. Or you drilled and blasted through solid rock, section by section, reinforcing as you went. Neither of those methods works underneath a river mouth. There's no solid rock down there. The ground beneath a river estuary is soft. Layers of mud, silt, clay, and loose sand, built up over thousands of years of sediment washing downstream. It behaves less like stone and more like thick, waterlogged pudding. Try to blast or dig through that the traditional way, and you invite disaster. Loose, waterlogged soil doesn't hold a tunnel shape on its own. Without something supporting the walls the instant they're exposed, the surrounding earth simply collapses inward. And with a river sitting directly above, a collapse doesn't just ruin the tunnel. It risks flooding the entire excavation instantly, potentially with workers still inside. This is exactly the problem that gave rise to a different approach entirely: the shield tunnel boring machine. Here's the basic idea, in plain language. Imagine a massive rotating drill at the front, chewing through the earth. Right behind that cutting head is a protective steel shell, the shield, that holds back the surrounding soil and water pressure the instant the ground is disturbed, before it has any chance to collapse. As the machine grinds forward, it simultaneously assembles pre-made concrete rings directly behind itself, lining the freshly cut tunnel wall before the shield moves on. By the time the shield has advanced past a section, that section is already sealed and structurally supported. The tunnel essentially builds itself, ring by ring, at the same moment the ground is being cut. It's a genuinely elegant solution to an extremely dangerous problem. But here's the catch, and this is where the story starts to escalate. Shield tunneling under a shallow canal or a modest river is one thing. Shield tunneling under a wide, powerful estuary for a distance of over 11 kilometers in a single underwater stretch, at depths where water pressure becomes a serious structural threat. That's something almost nobody had tried to do for a highway before. Every one of those factors, the distance, the width, the pressure, the geology, pushes standard tunneling equipment past its known limits. So if you actually want to do this, you don't use an existing machine, you build a new one. The machine built for this job is called Jianghai, roughly river and sea, a name chosen because this tunnel begins in a river and ends near open ocean. Some numbers to actually picture this thing: the cutting head alone is 16.64 meters in diameter and weighs 460 tons. The complete machine stretches 145 meters in length, weighs roughly 5,000 tons, and carries a total installed power output of over 11,000 kilowatts. Put that into something you can see in your head. A cutting face over 16 meters across is wider than a 5-story building is tall. The full machine, at 145 meters, is longer than most cargo ships that will be sailing directly above it while it works. Its total weight is roughly equivalent to more than 30 fully loaded jumbo jets, all packed into a single machine grinding forward beneath a riverbed. That makes Jianghai the largest shield tunneling machine ever built for a project like this. A machine so large, it had to be custom engineered specifically for this one crossing, because nothing off the shelf came close to what the job required. Think about what that actually means. This wasn't a case of buying advanced equipment and putting it to work. The equipment itself didn't exist yet. Engineers had to design and build a completely new class of machine before construction could even begin. And the ground this machine has to cut through is genuinely hostile. Muddy, silty clay, mixed with silt, layered with fine sand formations. Geological conditions the project's own engineers describe, carefully, as complex. The tunnel reaches a maximum depth of around 75 meters below the surface, at points facing water pressure intense enough that any breach in the shield, even a small one, could let water and unstable sediment flood in far faster than anyone could respond. And this machine doesn't get the luxury of stopping partway to fix problems or bring in support equipment. It has to complete a single, uninterrupted 9.3-kilometer drive for its portion of the crossing. One continuous run, underwater, through unpredictable ground without ever surfacing. That's the real engineering story here. Not a machine that's simply big, a machine that has to be big, precise, and completely self-sufficient for a distance longer than most entire subway lines, in one uninterrupted push underneath one of the most trafficked waterways on the planet. Here's where the scale of the full project comes into focus, because the underwater section is only part of the story. The complete tunnel runs 39.07 kilometers from end to end. Of that total distance, 11.19 kilometers is the section that actually crosses beneath the river itself. That means most of the route isn't the dramatic river crossing you'd picture. It's a long approach corridor on either side, built to gradually bring traffic down to tunnel depth and back up again. because you can't have cars diving straight down 30 plus meters underground in a few hundred meters. The transition has to be gradual enough for a highway to actually function at speed. The tunnel is designed as a full expressway, two-way, 6 lanes total, inner diameter of 14.6 meters, outer diameter of 16 meters. Design speed through the river crossing section sits at 100 kilometers an hour, rising to 120 along the rest of the route. Picture that inner diameter for a second. 14.6 meters across is wide enough to comfortably stack 3 lanes of traffic, plus emergency shoulders, plus the mechanical and ventilation systems required to keep a sealed underground roadway breathable for tens of thousands of vehicles a day. Because that's a problem people don't usually think about with tunnels. It's not just structural, it's atmospheric. A road tunnel this long, this deep, carrying this much traffic, has to constantly move enormous volumes of air through it, pulling in fresh air, extracting exhaust and heat continuously, because there's no natural airflow 30 meters under a riverbed. Ventilation shafts, fire suppression systems, emergency escape routes, structural monitoring sensors, all of it has to be built into a tunnel this long from the start, not added on afterward. This is the part of mega projects like this that almost never makes it into the highlight reel, but it's just as critical as the boring machine itself. A tunnel that can be dug is only half the challenge. A tunnel that can be safely operated for decades by thousands of ordinary drivers who will never think twice about what's above their heads. That's the other half. Let's walk through what's actually happened so far, because this project has been underway for years, and it's still very much in progress. Construction officially began in September of 2022, structured around a planned 6-year build. The Jianghai machine itself wasn't launched into the ground until April of 2025, meaning the years before that were spent on preparation. Shaft construction, approach tunneling, and assembling a machine of a size that had never existed before. By September of 2025, it had advanced past 1,600 meters into its drive, moving at an average pace of roughly 12 to 16 meters a day. Stop and think about that number for a second. 12 to 16 meters a day sounds slow, because it is. A car could cover that distance in under a second. But this machine isn't racing across open ground. It's grinding through unpredictable waterlogged sediment under a live river while simultaneously assembling a permanent structural lining behind itself, meter by meter, with almost zero room for error. By March of 2026, the tunneling had passed the halfway point of its drive, officially entering the main body of water beneath the Yangtze. Not near the riverbank anymore, directly underneath the open river. By June of 2026, boring had exceeded 6,000 meters, putting the project at roughly 64% completion of that drive. Run the math. If the machine needs to complete a 9.3 kilometer continuous run, and it had passed 6 kilometers by June of 2026, that leaves roughly 3.3 kilometers still ahead of it, all of it underneath the river, all of it requiring the same uninterrupted precision that got it this far. The project remains on track for completion and opening to traffic in 2028, closing out that original 6-year construction window. If that holds, somewhere in the next couple of years, the single hardest phase of this entire project, the continuous underwater drive, reaches its finish line, and the tunnel shifts from an active excavation into a finished structure, being fitted out for actual traffic. Here's the turn in this story, because on the surface, this looks like a regional transportation project, a shortcut between 2 cities. But that's not really what's driving something this expensive and this difficult. This tunnel is explicitly designed to accelerate what Chinese planners describe as a 1-hour commuting circle across the core of the Yangtze River Delta, the economic region surrounding Shanghai that includes some of the most productive industrial and financial territory in the entire country. Think about what that phrase actually means in practice. Right now, moving between certain points on opposite banks of the Yangtze near its mouth means either a long detour around to an existing bridge or a ferry that's slower and limited by weather and shipping traffic. This tunnel collapses that travel time dramatically, turning what might currently be a multi-hour trip into something that fits inside a single hour. That's not just convenient, it's economically significant at a regional scale. When you shrink travel time between 2 industrial and population centers that dramatically, you're not just making commutes easier. You're effectively merging 2 separate economic zones into one continuous labor market, one continuous supply chain. Workers who previously couldn't reasonably commute between these areas suddenly can. Manufacturers who previously treated these as separate logistics regions can start operating them as one. This is part of a much larger, deliberate strategy China has pursued for years, often described as Yangtze River Delta integration. The idea is to knit together the cities surrounding Shanghai, Suzhou, Nantong, and others into a single seamless economic superregion. Instead of a collection of cities quietly competing with each other, bridges have been one tool in that strategy for decades. This tunnel is the next stage of it, solving crossings where a bridge either can't work or carries too much long-term operational risk from weather and shipping. And once you see it through that lens, the tunnel stops being just an engineering curiosity. It's a deliberate piece of economic infrastructure, built specifically to erase a geographic barrier that's been limiting how this entire region's economy can grow. No project at this scale is risk-free, and it's worth being honest about where the real vulnerabilities actually sit, because they're not always the ones you'd assume from the outside. The obvious worry with any underwater tunnel is structural collapse or flooding during construction. That risk is real, which is exactly why the shield method exists. Sealing and lining the tunnel wall in the same motion as cutting it is specifically designed to minimize that exposure. It's a proven method used on other major crossings around the world, just never before at quite this combination of length, depth, and diameter all at once. The geology itself is the more immediate daily challenge. Muddy, silty, mixed sediment that behaves inconsistently as the machine advances, meaning engineers have to continuously adjust cutting pressure, support pressure, and grouting behind the shield to match ground conditions that can shift from one stretch of tunnel to the next. There's also a long-term risk that doesn't show up during construction at all, but matters enormously afterward. Settlement and structural monitoring over decades of operation. A tunnel buried in soft river sediment will experience gradual ground movement over its service life. Engineers have to build in sensors and maintenance protocols from day one to track that movement continuously, because a structure like this isn't something you build once and forget. It has to be actively watched for as long as it exists. And then there's the more ordinary risk that applies to almost every megaproject on Earth: schedule and cost. Complex tunneling projects, especially ones using custom-built equipment tackling never-before-attempted specifications, are notoriously vulnerable to delays when ground conditions turn out harder than modeled, or when equipment needs unplanned maintenance mid-drive. The 2028 completion target is the current official timeline, but it's worth remembering that timeline was set years before the hardest phase of construction. The continuous underwater drive was even fully underway. None of these risks are unique reasons to doubt this specific project. They're simply the honest list of what any engineer working at this scale has to actively manage every single day for years. What's proven right now is that the machine works. The drive is progressing, and more than half of the hardest section has already been completed successfully. What's still ahead is the remaining underwater distance, the fit-out of ventilation and safety systems across the full 39 kilometers, and years of operational testing before the first ordinary vehicle drives through. If you want to track whether this becomes the record-setting achievement it's being built up as, here's what actually matters. First, completion of the full 9.3 kilometer continuous drive. That's the single hardest engineering phase of the entire project. Once Jianghai breaks through on the far side, the most dangerous and technically demanding part of construction is effectively finished. Second, the second parallel tunnel bore. This is a twin-tube crossing, meaning the entire process has to happen again for the opposite direction of traffic. Watching whether the second drive goes as smoothly as the first tells you a lot about whether the hard lessons from the first bore were actually learned. Third, the ventilation, fire safety, and emergency systems fit out. Far less dramatic than boring through a riverbed, but just as essential, and exactly where less visible delays tend to quietly appear. Fourth, the official opening date. If the tunnel opens on schedule in 2028, watch the real traffic data in its first year. Whether usage actually matches the 1-hour commuting circle ambition this whole project was built around, or whether real-world behavior turns out more complicated than the planning documents assumed. Those 4 signals will tell you, far better than any press release, whether this becomes a genuine transformation of the region, or simply an extremely impressive engineering achievement that took longer than expected to prove its case. So step back from the tunnel itself for a moment. Here's the bigger pattern sitting underneath this story. This was never really about one road connecting 2 cities. It's about a country that decided the physical geography standing in its way, a wide river mouth, unpredictable weather, one of the busiest shipping lanes on the planet, wasn't a permanent obstacle, just a harder engineering problem than the ones that came before it. For decades, the answer to a wide river was a bridge. Now, in the specific places where a bridge creates more long-term risk than it solves, the answer has quietly become go underneath instead, and build whatever machine is required to make that possible, even if that machine has never existed before. That's the real story sitting underneath 39 kilometers of concrete-lined tunnel. Not a single crossing. A demonstration that geography, at this point, is being treated less like a limit and more like a variable, something to be engineered around rather than simply accepted. And once a country proves it can do that reliably at this scale, under one of the most difficult rivers on the planet, the next question isn't whether they'll do it again, it's where.